So these are common types of questions that we often ask. So this will either ask you for the energy difference when an electron and atom moves, or the wavelength of light of a photon released or required. So these are going to require similar equations, but they do look a bit different. So on exams, you guys will be given constants. So these are some of the constants you'll be given. This is the Bohr constant. That's what the lowercase b is for. Now, some things that you will not be given on exams, but are supposed to come from your brain, things you're going to need to remember, are things like the equation, which you would actually use Bohr for. So personally, I like to remember the energy level equation, which looks like this. Now, this is not going to actually help you a whole lot. You need to remember things also like the change in energy. So for change, this is where we need to talk about the in final, I still need all the other pieces, minus negative n squared initial. There are a lot of different varieties of this equation. So for example, I went ahead and put the z in there, but z is your nuclear charge. And we are almost always dealing with hydrogen, and at hydrogen that's just 1. So you are more likely to see this equation written without that. Then sometimes they'll go ahead and pull out b. Then no one likes double negative. And sometimes they'll go ahead and flip these two just so that the negative sign is in the middle. So realize that all of these are actually the same equation. They're just different forms and different simplifications of them. So I realize that this is nobody's favorite game with which equation do you need. This is also the reason why I won't tell you how many equations there are on the exam, because I just wrote 1, 2, 3, 4, 5 variations, and I could do a 6th, and I just remember this one. So it's up to you of how you want to think through this. Now, if all we needed is the energy difference, then this equation will work just fine for us. It will actually get us everything we need. Now, if we want to talk about the wavelength of light, though, we're going to need some extra ones. So we will need to be able to talk about how energy relates to wavelength. So we did talk about how energy relates to frequency, and then how frequency relates to wavelength. And you may have a combined version of this equation where we actually go ahead and solve for frequency to get rid of frequency in this equation. So you may have also seen one where we put our energy over Planck's constant equal to my frequency, and then basically plug that in there, and you wind up with something that looks like this. Oh, except nobody writes it like that because we usually want to solve for wavelength, and so usually it looks something like this. Or maybe we wanted to solve for energy, in which case it would look like this. So as you can see, the reason why these two questions may be difficult is not necessarily because the questions are hard to understand, but because this is a problem-solving game. So the first thing you actually have to do is figure out, first of all, do I need just the energy difference, in which case one of these will suit us just fine, or do I need to go all the way to wavelength of light, in which case I still need one of these, and then I need to be able to take the energy I have and get wavelength from the energy I have. So I'll let you guys ponder that. I'll go ahead and do a second half of the video just because we've already spent a lot of time talking about equations, but I'm probably going to use this one. And I actually like to go ahead and step through the transitions. So now that I have my two equations that I want to work with, well, 3 equations in my case, we're going to go ahead and actually solve the problem. Yeah, I know, we hadn't actually gotten that far yet. So I'm going to go ahead and copy my equations that I want to use. I'm going to hang out with b over here for a while. So this is then negative 1 over n final plus 1 over n squared initial. Sometimes something that gets confusing is which n is which. So notice this says an atom moves from into 2 in 1. So from is going to give you the initial point. 2 is going to give you the final point. So we go from 2 to 1. You can also think about this on our Bohr model atom, going from an n equals 2 down to an n equals 1. So we are in fact moving in that direction. So to solve for my energy, I'm going to have my Bohr's model constant. Negative 1 over n squared final is 1, plus 1 over n squared initial, which is 2. So I have b times negative 1 plus a quarter. For those of you who don't like negative numbers, you are welcome to use your calculator. This will give me negative 3/4 b. So notice I've just sort of kept everything together. So now that I actually have just that number, I'll go ahead and find b and get myself an actual value of energy. So it's going to be 2.18 times 10 to the negative 18th, I am in joules, times negative 3/4 in joules, because that's really the only unit I have right now. So this will give me energy. You'll notice also that this is a negative number. Negative in this sign, in this case, just tells me the direction I'm going. So I said earlier that we're moving from n equals 2 to n equals 1. This is decreasing in energy. Since my electron is decreasing in energy, that extra energy has to go somewhere. So since the electron is losing energy, that extra energy is going to come out. So since that energy is being released, I am going to release a photon. So since this is negative, this tells me that my electron is decreasing in energy. Since my electron is losing energy, that energy has to be released somehow. So since I've got to release energy, I'm in fact going to release a photon of sorts. So again, this negative sign is either going to tell me that energy is released or that a photon is released. As far as we're concerned, this is the same thing, because a photon's going to be, an energy is going to be released in the form of a photon. So if all I wanted was the answer to this first question, I'm actually finished. I found the energy. I found the energy difference. Also figured out what was the energy released. So I might be done. Depends on what the question was asking me for. However, it's also entirely possible that we wanted the wavelength of light. So if we wanted the wavelength of light, then we're not finished. So to get the wavelength of light, I'm going to take my energy that I have, and then there's a couple different forms of the equation that we could use. Now, since all we really cared about was with our energy is the direction, you can hang on to that negative sign, but realize that a photon, an actual wavelength of light, is not going to be negative. So all this really is released. So that negative sign does tell me something, but my photon is not going to be negative. My photon will only have a positive value. Wavelength, remember, is actually a unit of length, and saying that I have negative meters or negative nanometers doesn't really make a whole lot of sense. I know for you physics people it does, but in chemistry, we like things to be positive and then just give the direction. So this is my value of energy. What I am going to go ahead and do is just step through my equations, because I want wavelength down here. But I can take my energy, and again, I'm just going to go ahead and make it all positive. Energy is going to be equal to my Planck's constant. So again, constants are given. You don't have to memorize this number. You might wind up memorizing the number accidentally, but you don't have to. And this times my frequency. I'm going to hang on to extra significant figures. Makes me feel better. Since I'm dividing, my joules cancel. I should be left with inverse seconds, which is the unit for frequency. Remember, inverse seconds is also hertz. And I forgot, times 10 to the positive 15th. Don't lose your exponents, ladies and gentlemen. It's very easy to forget your exponents, but don't lose those. You need those. Okay, we're almost there. I want wavelength, I have frequency. So now I'm going to go ahead and use my speed of light. So speed of light is also given to us. 2.998 times 10 to the 8 meters per second is going to be equal to my wavelength times my frequency. So on my calculator, when I did this, I got this number. This is really annoying. So what I'm going to do instead is I'm going to hit second and this degree, which above it says science engineering, and it's going to give me the option to go into scientific notation. So without actually having to move my pen all along my calculator, I can actually get the number that this is. Now, I should actually be in meters. My speed of light had a unit of length, so this is actually in meters. Oftentimes the problem will call for nanometers, so realize we can still take this number and go from meters to nanometers. If you're curious about significant figures, because we had n equals 2 and n equals 1, these are actually exact numbers. Remember, we can't actually have energy levels that are half energy levels. So this 2 and 1 are actually exact numbers, which technically means that my significant figures are limited by my constants. So this 121 should actually be limited to 3, which is due to my constants. It's kind of a strange situation, but in case you were curious, that is how that works. Hopefully this helps. Do practice this. I know there's a lot of steps. The other thing I will tell you is that there's not a whole lot of shortcuts to this problem. So if you see this on the exam and it's problem number 2, you might skip it because there's shorter, faster problems that we also ask you to do.